This is Ashley Baranzuk, Sydney Jackson, and Sammie Volkamer's Unit 8 presentation. An intro into confidence intervals. Key terms to know: point estimator is a statistic that provides an estimate of a population parameter, and point estimate is the value of that statistic from a sample. An ideal point estimator will have no bias and low variability. All confidence intervals we construct will have a form similar to estimate plus or minus margin of error. An example from the book: a C% confidence interval gives an interval of plausible values for a parameter. The interval is calculated from the data and has the form point estimate plus or minus margin of error. The difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. The confidence level C gives the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. Interpreting confidence levels and intervals. A confidence level tells us how likely it is that the method we're using will produce an interval that captures the population parameter if we use it many times. The confidence interval also gives us a set of plausible values for the parameter. The sample mean will vary from sample to sample, but when we use the method estimate plus or minus margin of error to get an interval based on each sample, C% of the intervals capture the unknown population mean. When calculating a confidence interval, we say that we're confident that the interval from blank to blank captures the actual value of the population parameter in context. When interpreting confidence levels, we say we're 95% confident, which is shorthand for if we take many samples of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. Constructing confidence intervals. When calculating a confidence interval, we use statistic plus or minus critical value times standard deviation of statistic, where the statistic we use is the point estimator for the parameter. Properties of confidence intervals. The margin of error is critical value times standard deviation of statistic. The user chooses the confidence level, and the margin of error follows from this choice. The critical value depends on the confidence level and the sampling distribution of the statistic. Greater confidence requires a larger critical value, and the price you pay is a wider interval. And lastly, the standard deviation of the statistic depends on sample size n.
Alright, my slides are going to be over one sample Z interval and one sample T interval, and explaining how to find both of those and kind of the difference between the two of them. Okay, so we're going to start off with some important Z-scores to know. The first one is 1.96. This is when the confidence interval is 95%, and this is probably going to be the most common one. It's just important to know these, that way you don't have to look through the table every time. And then another important one is going to be 1.645 when the confidence interval is 90%. And then here's the equation for standard deviation. It's going to be sigma equals the square root of p times 1 minus p divided by n, and that's all going to be under the square root. But in this case, since we don't know p, we have to replace it with p hat, which gives us the standard error equation, which is basically the same, just instead of p, it's p hat. And then here are the conditions for conducting a confidence interval. First one is going to be random. You have to make sure that the data comes from a random sample or a randomized experiment. You have to check the 10% condition. So that means you have to make sure that you're sampling less than 10% of the population. You can check that using this equation. 10n is less than or equal to big N. And basically the difference between those n's is that n is just the sample, big N is the whole population. And then you also have to check for normal/large counts. So that means you have to make sure that n times p hat and n times 1 minus p hat are both at least 10. And then here's going to be the basic equation for finding your confidence interval. So when conditions are met, a C% confidence interval for the unknown proportion p is p hat plus or minus the critical value, which is going to be a z-score in this case, times the square root of p hat times 1 minus p hat divided by n. And once again, that whole second half is going to be under the square root sign. And then next we're just going to go over a 4-step process for a z interval. So you're going to start off by stating. This is where you're going to list your parameter that you want to estimate and the confidence interval that you're estimating at. Then next step is plan. Here you're going to check your conditions, the random, 10%, and the normal, and you're going to identify the appropriate inference method. So in this case it'd be one sample z interval. Next you're going to do, which is where you're going to perform your calculations using the equation I just showed. And then conclude, you're going to interpret the interval in the context of the problem. Next is going to be one sample t-score for a t-interval. And basically the difference is when the data is standardized using S sub x instead of sigma, the statistic now has a t-distribution. So that means you're checking a sample rather than the whole population. And then to find the statistic, you're going to use t equals x bar minus mu divided by S sub x divided by the square root of n. And then finding degrees of freedom is pretty simple. It's just n minus 1. So it's your sample size minus 1. And then the conditions are basically the same. You have to make sure it's random, which means that it comes from a random sample or randomized experiment. You have to check 10% again. And then for the normal, it's slightly different. You have to make sure that the population has normal distribution or that the sample is large enough to use the central limit theorem. So that means that the sample would have to be greater than or equal to 30. If the shape is unknown and n is less than 30, you have to use a graph of sample data to assess the normality. There must be no outliers or strong skewness, or else you can't use the test. And then here's going to be your basic equation for a t-interval. So when the conditions are met, a c% confidence interval for the unknown mean mu is x bar plus or minus the critical value, which is going to be a t-score in this case, times S sub x divided by the square root of n. And then next we're going to go over the 4-step process. So it's basically the same as for a z-score, except you're going to be stating the mean that you're trying to find and the confidence interval rather than a proportion. To plan, you're going to check your conditions again, identify your appropriate inference method. In this case, it'll be one sample t interval. Then you're going to do, which is where you perform your calculations using the equation that I showed. And then conclude, you're going to interpret your interval in the context of the problem.
So the third type of confidence interval is the two-sample z-score. So the sampling distribution for the difference between two proportions is this, p hat 1 minus p hat 2. That's the standard deviation equation. That's the mean equation. So the conditions to check for this kind of confidence interval. Random, you just want to make sure that both samples are chosen randomly or they are independent of one another. That's usually stated in the problem. For the 10% condition, you want to make sure that your sample size is less than 10% of the population so that when you're sampling, you don't repeat samples. For determining if it is approximately normal, you want both samples to be NP and N times 1 minus P, or at least 10. You want to do that for N1 and N2 for both of them. For these, you want to make sure that you state that both samples are random or they meet the 10% condition or are normal for all of them, because we are talking about two different samples. The standard error is when we don't know the values of the parameters. The confidence interval equation for P1 minus P2 is this equation where Z star is the critical value. So the 4-step process for this, you start with state. You're going to list what P hat 1 and P hat 2 mean in terms of the problem. You're going to give the proportion number and the sample size, so whether it's a percent or a decimal, and you're going to give that. And then you're going to state what confidence level you're testing at, whether that be 95%, 90%, whatever it is, and then what order you're finding the difference, whether it be P1 minus P2 or P2 minus P1. For the plan step, you're going to check the conditions that we mentioned in the last slide for random, 10%, and normal. And then once all of those are met, you're going to say all conditions are met, so proceed with the two-proportion Z interval. For the do step, you're going to solve the problem using the formula. And then for the conclude step in complete sentences, you're going to state your confidence between what interval in terms of the problem situation, the confidence level that you tested at, and then a little detail about the problem and where your numbers are coming from. So the fourth type is the two-sample t-score. The sampling distribution for the difference between two means is x bar 1 minus x bar 2. The standard deviation and the mean. The conditions to check for these: random, you want to make sure that both samples were chosen randomly or that are independent of one another. You want to make sure that the 10% condition is met so that your sample is less than 10% of the population. And then you want to make sure that normal, this one's a little bit different, so you're going to check the central limit theorem, and you want to make sure that your sample is greater than or equal to 30. And if that's not the case, you can try to graph it. You can either make a histogram or a dot plot or different kinds of graphs, and you just want to make sure that there's no outliers in the graph and that the graph isn't skewed. So, checking the confidence interval, it's x bar 1 minus x bar 2. You're going to use that equation where t star is the critical value. When you determined the t star, you want to use the degrees of freedom for n minus 1. And then if the sample sizes are different between n1 and n2, you're going to make sure to use the smaller size to be more conservative with your answer. And then tips for this one, you want to try to use equal sample sizes if you are creating a problem like this, so that n1 and n2 are equal. And then you don't want to use paired data for this type of confidence interval. So the 4-step process for this: state, you're going to list what mu1 and mu2 mean in terms of the problem situation. You're going to give the sample size x bar 1 and x bar 2 and then the standard deviations for both samples. Then you're going to state what confidence level you are testing at and what order you are finding the difference. So whether that be mu1 minus mu2 or mu2 minus mu1. Then you're going to plan, you're going to check the conditions like we said in the last slide, and then if they're all met, you're going to state all conditions met, so proceed with the two-sample t interval. For the do step, you're going to use the equation. And then for the conclude step, complete sentences, you're going to state what confidence level you tested at and between what interval in terms of the problem situation.